Okay, so let us continue the discussion on compressible flow. So, we are looking at the relationship between Mach number and the velocity, and this is what we stopped at in the last session, where you get the relationship between Mach number in the local velocity. Now, just we derived that equation 6, but some points here to be noted which are important is that at A star can be designated as A star. Similarly, at B it should be A B star. So, if the flow is not adiabatic between A and B, then A star would not be same, or if the flow is adiabatic everywhere, then A star would be C. For isentropic flow also A star would be C. Now, if we return to the stagnation conditions, like for U, P, T density like that. Now, let us say consider the fluid. Let us consider the fluid at A, which is point 1, equation 4, and this fluid is brought to rest isentropically at, so brought to rest at point 2 of equation. So, what will happen then? U2 equals to 0, P2 will be P naught, T2 would be T naught, and something like that. So, from equation 4, which is true for both adiabatic and hence isentropic flow, we can write Cpt plus U square by 2 is Cpt naught. So, that is what you can write, and you can further simplify. T naught by T is 1 plus U square by 2 Cpt, which is 1 plus U square by 2 gamma RT by gamma minus 1. If we simplify a bit further, what we get? 1 plus gamma minus 1 by 2 U square by A square. So, this will have T naught by T 1 plus gamma minus 2 by m square. So, that is equation number 8. Now, if we say the process is isentropic, then what we can write, that P naught by P is T naught by T gamma minus 1, which is rho naught by rho to the power gamma. So, this is P T rho relationship for isentropic flow, and once we put it back in equation 8, this gives another relationship for P naught by P is 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1, which is 9, and another 1 on density rho naught by rho 1 plus gamma minus 1 by 2 m square 1 by gamma minus 1, which is 10. So, all these relationships we get. Now, the actual flow field does not need to be isentropic to calculate P naught, T naught, rho naught, etc., because these are imagined and defined quantities. If the flow field is non-isentropic, that is it. If non-isentropic, that means non-adiabatic and or irreversible, then what will happen, T naught A is not going to be equal to T naught B, P naught A, similarly for rho. So, these properties are not going to be same. Now, if the flow field is isentropic throughout, if let us say isentropic throughout, then P naught, T naught, rho naught, these are constants. Okay. So, then from equation 5, what we can write, A 1 square by gamma minus 1 plus U 1 square by 2, A 2 square by gamma minus 1 plus U 2 square by 2. If let us say if 2 refers to stagnation or conditions, then what we get, A square by gamma minus 1 plus U square by 2 equals to A naught square by gamma minus 1, that is equation 11. Now, from equation 6 and 11 we get gamma plus 1 by 2 gamma minus 1 A star square equals to A naught square by gamma minus 1. So, in the other way one can write A star square by A naught square equals to gamma R T by T naught, which is T star by T naught 2 by gamma plus 1. So, if we put gamma equals to 1.44, this would be roughly 0.83 equals to, if we use for gamma 1.4. Now, again for P naught by P, we will use the relationship, and rho naught by rho, which is 1 minus gamma by 2. So, what we get, since P star, rho star are defined at m equals to 1 condition, we get P naught by P star equals to 1 plus gamma minus 1 by 2 gamma by gamma minus 1. So, which means P star by P naught 2 by gamma plus 1 by gamma minus 1, which would be 0.528 for air. It is also the critical pressure ratio. Now, if P by P naught is less than critical pressure ratio, then the flow is supersonic flow. Okay. Now, in the similar way we get for rho star by rho naught, which will be 2 by gamma plus 1, 1 by gamma minus 1, which would be 0.634 for air. So, these are the now finally we consider equation 6 again, and what we can write is a square by gamma minus 1 plus u square by 2 gamma minus 1, which is a star square. Now, we divide by u square. So, you can write a by u square by gamma minus 1 plus half gamma plus 1 by 2 gamma minus 1 a star by u square. So, which 1 by m square by gamma minus 1 gamma plus 1 2 by one by m star whole square minus half. So, this gives a fantastic relationship between m and m star. So, this m square equals to 2 by gamma plus 1 by m star square minus gamma minus 1. So, this is a relationship that you get between m and m star. Now, if m equals to 1, then m star also becomes 1. If m is less than 1, which is subsonic, so m star also less than 1. If m greater than 1, m star also becomes greater than 1. If m tends to infinity, m star tends to gamma plus 1 by gamma minus 1. So, these are the correlation that you can obtain from the m and m star relationship, and this is for 1D dimensional steady compressible flow you can derive. Now, moving ahead, so we'll other thing that we will talk about is the normal shock relations. Okay. So, the first question which comes to somebody's mind, what is shock wave? So, that is an very pertinent question. Now, a single way one can answer that shock wave is a discontinuity which is a of very thin region in the flow field of a supersonic flow across which the flow properties change drastically. So, means this is a discontinuity in the flow field which is of a very thin region, order of 10 to the power minus 5 6 centimeter, depends on the geometry and the condition in a supersonic flow across which the flow properties changes drastically. Now, this can be seen or measured in Schlieren photographs or images because of, so can be measured or seen in Schlieren photograph because of density variation. Now, shock waves can travel. So, shock waves can travel, for example, shock tube, sonic boom, these are the example. Almost explosive compression process, so there is a dramatic increase in pressure. Now, let us see how. So, you have a object inside the flow field. So, these are the pattern of the streamline. Let us say m infinity is less than 0, less than a infinity. So, this is how we can define how shock waves are formed. Okay. So, we consider a flat plate, or rather this object, this is mounted in a flow, and the flow field consists of individual molecules, some of which impact on the face of this let us say cylinder. Now, in general there would be change in molecular energy and momentum due to impact. Now, this change in momentum is seen as an obstruction by the molecules. So, then the fluid particle will sense there is an obstruction sitting there, and because of change in that momentum. Now, the random motions of these molecules communicate this obstruction to the other region of the flow through collision. That means, with the through the molecular collision, this presence of this object is being communicated to the other region. So, the presence of obstruction is propagated everywhere, even upstream, by sound waves. So, this is very important, that the presence of the obstruction is propagated everywhere, even upstream, by sound waves. Now, this is where the situation, if the incoming stream is subsonic, like V infinity is less than A infinity, then the sound waves can work upstream and convey the presence of this body to the fluid particle sitting here. So, from this to this position, this information can be passed, and the flow properties and the flow field change accordingly to accommodate these changes, and that is why you can see the streamlines goes like that. Now, this is all right if the upstream condition is this, but if the upstream condition is supersonic, then what will happen, this sound wave cannot propagate from this position to the upstream position, and the information of this presence of this body cannot be passed to the point which is sitting in the upstream. So, this cannot no longer propagate upstream. Instead, what will happen, they tend to coalesce a short distance ahead of the body. So, if the body is here, around a short distance ahead of that they will coalesce, and this coalescence of the waves form a thin shock wave. Okay. So, this is what happens when the flow field is supersonic and there is a body which is placed inside the flow field, then the informations of this presence of this body cannot be passed to the upstream, and then the shock wave is formed. And there could be two types of shock waves, one could be normal shock wave, other one could be oblique. Now, in normal shock wave, it is perpendicular to the flow field, and this is very strong, or rather strongest shock waves. Now, flow behind the normal shock waves is also subsonic. Let us say if you have a normal shock here, then this is upstream, which is greater than 1, then this is downstream. So, this would be subsonic. So, the upstream flow does not know about the presence of shock waves, hence the flow properties have to change abruptly across this shock wave to adjust this variation between upstream and downstream. So, this is what shock wave is all about, and how shock wave is formed and all this. Now, we will look at the normal shock relations. So, normal shock relations will have this small shock, let us say. So, U1, rho 1, T1, P1, M1. So, this is stagnation 1, and this is U2, rho 2, T2, P2, and M2 less than 1, this is 2. So, these informations all are known, and downstream information are sort of unknown. Now, again the situation here is, this is 1D flow, steady adiabatic flow, shaft work and neglecting potential energy. So, these are the some of the assumptions which are associated, so that we can derive the simple equations. Now, whatever we have done, so that we can use derived equation 1, 2 and 3 directly. So, what we write, rho 1 u 1 equals to rho 2 u 2, that is from continuity. So, let us say equation 14 or mass conservation equation, and we can write P 1 plus rho 1 u 1 square, P 2 plus rho 2 u 2 square, which is momentum, that is 15, and u square plus u 2 square, which is energy, that is 16. Now, we assume perfect gas, so that we can write P equals to rho r T and H equals to Cpt. So, what we have? We have 1, 2, 3, 4, 5. So, number of equations are 5 and unknowns are 6. So, what we will do? We will divide 15 by 14, and what we get, P 1 by rho 1 u 1 minus P 2 by rho 2 u 2. Again you have A is root gamma r t. So, A square is gamma p by rho, or p by rho is A square by gamma. So, if you use that, this would becomes gamma u 1 minus A 2 square by gamma u 2 minus u 1. Now, from equation 16 we get A 1 square equals to gamma plus 1 by 2 A star square minus gamma by 2 u 1 square. So, what you can write, A 2 square equals to gamma minus 2 by A star square minus u 2 square. This is happening because since the flow is adiabatic, A 1 star is A 2 star. So, we can get gamma upon 2 A star square by gamma u 1 by 2 gamma u 1 minus gamma plus 1 by 2 gamma u 2 u 2 minus u 1. So, further if we do the little bit of mathematics, what we get finally is A star square equals to u 1 u 2. So, this is equation number 19, and this relationship is known as or called as Prandtl relation. So, this is Prandtl relation. Okay. So, this is a very important relation for normal shock, where you get this ester and the velocity upstream of the shock and the relationship between the both the upstream and downstream velocities. So, we can see how one can obtain this, but we will continue that discussion in the next lecture. So, we will stop it here.